Okay, so welcome back. So before the next talk, let me remind something. So you know that not only when you organize conferences, you are always trying to avoid problems, but we are actually in the opposite situation now. So we are actively looking for them. So this is related to the open problem and question sessions for tomorrow, for Thursday, sorry. So we invite everybody of you who has interesting open questions on problems and is happy to share to contact one of the organizers. So maybe let's say before tomorrow morning in the coffee break so that we can collect the list of suggested problems and organize the sessions accordingly. Okay, thank you. Otherwise, let's go on with our plan. So next speaker is Farbod Chokrier from University of Washington. So he is delivering the second lecture of the series Berkovich spaces, tropical geometry and number theory. Please, Farbod.
Can you hear me? Okay, thank you. I would like to also thank those of you that engaged after my first talk. It was mostly positive feedback, but I really appreciate more feedback as I continue to polish my notes for the rest of the week. Let me start. So my plan today is to finish up the discussion on heights. In fact, the part that I said yesterday is a global picture. I want to focus on local pictures because I want to do tropical geometry or Berkovich spaces. But before that, I'll give some philosophical explanation of how geometrically one should think of heights and why doing things locally can be done, hopefully can be done geometrically. But the first thing, there was a very good question yesterday, which the answer I didn't know, and the answer that came up was not correct. Let me just, I have already explained it privately to people that were interested, but for the record, the kernel of the height machine, kernel of height machine, what line bundles give you trivial heights is exactly equal to torsion line bundles, which is line bundles that some power of them in Picard is going to be trivial. So L to some power is the trivial line bundle, or in the language of divisors, some multiple of the divisor is principal. It's actually, most books actually don't discuss this, but Serre has a beautiful book on lectures on Mordell-Weil. I think it was page around 47 or something, 48. 3 pages of proof, and it's not trivial, so I don't feel too bad that I didn't see it immediately. One direction is actually easy. If a multiple is trivial, then by homomorphism you can see that immediately it should be zero height function, but the opposite direction needs some work. Okay, I don't need this. I just wanted to correct the record because the question was arised. Okay, let me say just a few things about local heights, which is more directly related. So local contributions to heights. I guess as Kumars would put it, even before kindergarten, you realize prime factorization is important. And if you go to a sufficiently good kindergarten, you realize it's not just prime numbers that you should care about. There is also a sign that you should worry about. The Archimedean prime is also important. For any positive integer, primes are enough. But just to say positive, you have to use the absolute value to detect whether something is positive or not, the usual absolute value. In other words, -6 is -2 times 3, and this minus information is something more than just being prime number. So how does this relate to so-called, well, let me say a few things. So global quantities as global, like this 6, or the type of height functions that I was describing, like h hat d function, the canonical height should be made from local quantities. Should be made from local. By local, I mean if your field is, for example, Q, maybe you have to have prime numbers, and I was alluding to some extra information, maybe local quantities. So one for each, let's say in the example of k equal to q, you want one quantity for each prime p, and also a little bit more. I'm going to put the infinity here, but this is the usual absolute value. The so-called places of Q. I'll come back to this more geometrically in a moment, but let me say actually a theorem of Néron, which is directly related to the height function I finished the lecture yesterday. So a theorem from 1960s. And in fact, many people have heard of Néron in the context of Néron models. I learned recently he actually constructed those models for abelian varieties to prove a theorem like this, which most people actually, it's such an important contribution that has found many different applications, and many people that use Néron models never cared about heights, but this was the original motivation. So let V be a place of K. So these are places in the case of Q. And in general, you should think of equivalence of absolute values you can put on your field. For any P, you can have a p-adic absolute value, and you have the usual absolute value. And you can discuss these things more generally for number fields and even function fields. Then he proves the following fantastic statement. There exists a unique well, up to constant, up to, again, yesterday we had up to bounded functions, and it was annoying. Constants are not as annoying, but they're still annoying. But we'll come back to this. Up to constants. Function which I will use for now, lambda d. D is the divisor, so d was, let me actually remind you, I want to talk about the situation of yesterday. A is abelian variety. Over K. D is a symmetric divisor, for example. Symmetric effective. And I remind you from this data, I had this H, D, the canonical height, or one might call Néron-Tate height. So this is the same D as in yesterday, but it's now attached to the place P. And then you get a function which is on the KV valued points. This is the V-adic completion. So if you are with the usual absolute value, I'm talking about R or maybe C. And if you are over primed, I'm talking about p-adics. But then you have to remove the support of D to real numbers. So there is such a function, which essentially is the decomposition, gives you the decomposition of the H hat. So I'll write that at the end, but this function already when you're focusing on V, the place V is nice. I won't list all the properties it proves, but maybe one thing that is going to be motivating for us, this is continuous. actually think about what that means as I'm writing the other parts. Then there are some other niceties that I will list, but it's not super important for the rest of the lecture. It's additive with respect to D, and of course up to a constant. I might drop V because I'm focusing on V anyway. It's functorial with respect to isogenies, with respect to isogenies, meaning if you have an isogeny between A1 and A2 and you pull back, you get the right equalities with composition. But part D is the point that I want to make is this is actually giving you a decomposition. Just like the product formula for 6, this gives you a decomposition of the global quantity. Up to a constant, minus some global constant kappa. Well, I mean, I was talking about product formulas, and now I'm doing addition, but remember there was a logarithm involved. So product turns into summation when you take logarithm. This is really a decomposition, as you know from kindergarten. And also, I do care about the place at infinity for the reason that you should care about signs when you factorize. Of course, this only makes sense when you are not on the support of the divisor, because the function is not necessarily defined over the support. And there is a good reason coming from Berkovich spaces that this is the right thing to do. You should think of this actually as some kind of a distance from the support. So some kind of distance. It's a good intuitive way of thinking about it, but it is, in fact, a precise way to think about it. So I'll say some things about Berkovich spaces that makes this into a correct statement, not just a philosophical thing. OK.
Do you really want to use letter K for constant?
This was supposed to be kappa. But I don't know how to write kappa. Is this kappa-looking thing? OK. All right, this is something that I definitely would like to come back to after I discuss Berkovich spaces. And in fact, one can describe this function in terms of very beautiful combinatorial objects. He used Néron models. I don't want to discuss his proof, but he actually had 3 different really interesting computations. So he gave a Tate-like construction, a Tate trick construction. That's one way. But his most conceptual proof, which gave a more sort of better picture, was using Néron models. Well, he didn't call them Néron models. Maybe he called them minimal model. And then in the case of Archimedean places, V Archimedean, he actually gave a formula in terms of theta functions. So if you know a uniformization of complex abelian varieties, there is a beautiful way of describing global sections of line bundles attached to the divisor here. So you can, at least in principle, the polarized case, there is even a canonical choice. And then he gave formulas for that in terms of theta functions. And maybe now that I started, let me continue the history. In the non-Archimedean place, this was wildly not understood until Tate gave also a flavor of non-Archimedean geometry, rigid analytic geometry. And then for Tate curves, for Tate elliptic curves in dimension 1, he tried to do what Néron had done. And he was successful in giving a formula in terms of theta functions for this function when A is one-dimensional. And oddly, also, there was some mention of Bernoulli polynomials. I'll one of my goals is to actually revisit that computation and explain it from tropical point of view, how that computation fits into the kind of stuff that we do. Any other questions? So this sort of wraps up the motivation from number theory. Now I want to switch to Berkovich spaces, which allows me to study these functions locally. But before that, let me just end the height theory by saying that there is actually a more geometric way of doing height theory. Heights, in a way, are just degrees. But I have to say what that means. So this is kind of a remark, but very vague, and I hope this will serve as an advertisement of an area which is fascinating and difficult to learn. Arakelov's geometric view of heights. And this is by no means is going to be, I don't say anything concrete really, I just give some general explanation why theory that Arakelov started is beautiful and useful. So let's say you have a bunch of equations with integer coefficients or maybe rational coefficients, you clear the denominators. You can think of this as a scheme or variety over spec z. And you would so spec z is some kind of a one-dimensional object. And you would like to think of this as a one-parameter family. Which is fine. But when you want to do actual computations, the kind of things that geometers do is maybe you have a line bundle here, and I'm thinking of the divisor that I've been using all the time. And maybe you want to bring it here and then compute some degree or something and get some number out of it by pushing it down. And then immediately you get worried because if you want to compute degree or you want to do intersection theory, in the geometric case, you have a proper object here, and intersection theory makes sense. But spec z is some kind of affine object, and it doesn't make sense to do intersection theory on that. And that's where Arakelov comes in. So a problem. There are actually two problems, but one of them both of them are actually not unrelated to the subject of this workshop, but one of them is focus of my lecture. I'll say very quickly what other problem is, or problems. Number one is that spec z is not in any natural way compact or proper. And then he had this brilliant idea that spec z is just the collection of, as a set, let's say this is the collection of primes. Spectrum of a ring is just a collection of primes in that ring. And then he said, well, spec z, so I can think of primes as being p-adic absolute values. So something is missing. As you learned before kindergarten, you need the infinity as well. So he said, you have to compactify this. So compactify. I'll put a hat by just putting infinity next to it. OK, well, you can do that, but then what do you do with it? It turns out, so you want to do intersection theory. He had all sorts of brilliant ideas of, he did this in the case of curves, but it's been generalized by many people. I can't possibly make a list because I didn't prepare, and also there are many people involved in this theory. But what he did was he said, OK, I'm going to do the usual algebraic geometry over spec z, but whenever I want to use this, whenever there is a sort of something is spilling over because things are not proper and going to infinity, I'm going to fix that by doing some analysis here. So at infinity, analysis comes in. In fact, Lang has a book on Diophantine geometry, and he has a mischievous sentence. In this way, analysis is degenerate number theory. But the dream would be, and the dream that is related to this course and to this audience would be, maybe you should also do analysis in prime numbers. Maybe that's not a crazy idea. Now we have spaces that are ready to do analysis at finite places as well. And that's what excites me about Arakelov geometry. I should say it's a huge field, and I'm no expert, but the direction that comes from doing analysis over p-adic numbers is very fascinating to me. So let me just wrap this up by saying that, maybe I'll just write here that you get a nice intersection theory. Using this idea, and then maybe the dream is, at least my dream, but it's not just me, maybe we should also do analysis over finite places. And the rest of the lecture will be related to what do I mean by analysis. Very quickly, in passing, because it's not related to my lecture, I said problems. That was problem number one. Problem number two is another thing which does relate to this industry of F1 geometry, which is not unrelated to some of the work people do in matroid theory these days, is that when you have a family over a proper curve, so this over some field, then you can further push things that you have, you can further push down to the spec K. So maybe you want to have vector spaces over K out of this information upstairs. But we don't have anything below spec Z. And that's where F1 geometry and things like that might be related. So this is not my area of expertise for sure, not even interest, but I just want to say that the idea of trying to prove Riemann hypothesis or doing all sorts of things over F1 comes from this other problem when you're doing arithmetic. So maybe X over spec Z, what should you put here? And I'll leave it at that. I don't have anything intelligent to say. I do know that people are trying, and in some cases even getting big grants to do this. Okay. With all that, I'm going to now focus on analysis over finite places, which is closely related to tropical geometry. Any questions before I switch gears? Sorry, I don't see who is talking. Yes?
This Arakelov geometry setting, do we also have like a scheme structure or this thing, or is it just like...
No, I mean, okay, there are other experts, please chime in. The category is not well understood. It turns out that you can pick Fulton's book and put hat on everything that you see, well, not everything, but many things that you see in Fulton's book on intersection theory, you can put a hat on, but it's still a work in progress to make sense of many of the things happening, sort of. There's no nice category that things are happening.
So the primary field, you just take like a complex point?
Yes, you take the complex points, you put, if you have a line bundle, you pick a Hermitian structure on that, Hermitian metric on that, and then you do algebra plus analysis. And what I was saying about the dream is that maybe this is written actually as a dream in Soulet's book in Introduction to Arakelov Geometry. There is some paragraph that says the dream would be that one should do analysis everywhere. But at least at the birth of the theory, these non-Archimedean analytic spaces were not as well studied. But of course, some shadows of those theories have existed. And actually, one of my goals would be, Néron already in the 60s was doing a shadow of tropical geometry. So this function actually has a tropical explanation, which I will come back to. Any other questions? Okay, very quick introduction to Berkovich spaces. And my main goal is to say how tropical geometry could fit in, at least in the case of curves and abelian varieties, which is the focus of my lectures, very nicely fits into this bigger picture. And in general, tropical geometry can be thought of as studying skeletal of Berkovich spaces. Okay, now I'm going to have a field with an absolute value. I could, for the first part of this title, I could assume this is just complex numbers and usual absolute value on complex numbers, but you just recover complex geometry from that. I'm going to say it's a non-Archimedean absolute value. Non-Archimedean, it means the triangle inequality is even better or worse, depending on what you like, than instead of putting x plus y, I put max of the two. Say it again? Trivial is allowed. In fact, the trivial theory of Berkovich spaces is highly non-trivial. You get interesting results by working with that. In fact, that was the next thing. So if you want to do number theory, as I am trying to convince you, this is a choice. So this is example with the p-adic absolute value. So this is the completion of Q with respect to p-adic absolute value you can put on Q. And p-adic absolute value is nothing too mysterious. If you have any rational number, you can factor out all the primes that you have, and then say the p-adic absolute value of that. There's no p left here. Let me just be a little bit imprecise. You can announce that the higher power of p that you have, the smaller the number is. And then you can complete Q with respect to this absolute value the same way you complete Q with respect to the usual absolute value. Look at Cauchy sequences modulo equivalence. And equivalence is when Cauchy sequences get close to each other. Similar to the context of the previous lecture, you might want to degenerate things. You might want to work with this, with t-adic absolute value, which remembers the leading term, leading coefficient, leading exponent. So these are formal Laurent series. And you want to send t to 0, as it was the case. You had a punctured disk, and you wanted to see what happens when t goes to 0. Or you could think of algebraic closures of this, completional algebraic closure of these Puiseux series, formal Puiseux series, things like that. They all come from, so these are useful for geometry and deformation. This is useful for number theory. Any field K with the trivial absolute value is a very useful example, and trivial means brutal. If x is 0, I have to put 0, but otherwise I'll put 1. And in fact, my best selling point would be the last example, any field with absolute value, except for two weird fields, R and C. Those are really weird. They're Archimedean. The only complete Archimedean fields in the world are R and C. This is a theorem of Ostrovsky. So they are very weird. If you find the field in the street, it's going to be non-Archimedean. If it has absolute value and is complete, and they better be complete. So any complete field. well, except for these pathological examples. Sorry, I'm of course joking. In fact, the theory of Berkowitz spaces does use this weirdo R. When I say complete, I mean, sorry, I know many of you are algebraic geometry and probably don't remember analysis. Complete means Cauchy sequences converge. I already used it. It doesn't mean proper. Okay, so what's the problem that we need to fix? Okay, so I have some variety over this thing, and I want to do analysis. And you do it very easily over C or R. In fact, Calculus 1 is already starting to do analysis. So if you have a variety X over C, and let me have a running example, X is A1. What you do is, well, you look at the C points, and my running example will be just C. But algebraic geometers put a very weird topology on this. You don't want on C to look at Zariski topology, but that's what we do. So this is with Zariski topology. But here, Zariski topology means it should be, okay, empty and C, but otherwise open sets should be cofinite sets. So this is open is cofinite, well, more or less, except for infinity and, C and empty set. But I hope you all agree this is not the topology you want to do in complex analysis class. So you change your point of view. So to do analysis, you change this and you say, use absolute value on C and define analytic topology. By that, I mean define balls. Let's say over C in the running example. And this should be the basis for your topology. A set is open if for any point in that set there is a ball which is contained in the set and things like that. The point set topology stuff. Okay, and we are kind of lucky that once we completed Q and we went to R, already this was okay. You started doing calculus. You had a very nice underlying topological space. It was connected, and you could do analysis. You could take integrals. You could talk about measures and things like that. And in the complex case, things are even nicer. But this doesn't work. This does not work in real world. By that, I mean except for those two examples. For K not equal to R or C. The issue, let me actually say one of the core issues is that any point in a ball is the center of the ball. So it follows from the triangle, the strong triangle inequality. If B is in, take the same definition, just put K here, use your absolute value. If you have a point in a ball, then it's the center of the same ball, which I don't expect you to imagine. It's crazy that any point in a ball is the center of the ball. The proof of it is super easy. Just write down this statement and use ultrametric inequality. You see, you always get this equality. But it's weird and it has severe consequences. In particular, essentially this, but you might prove it more directly. Even in my running example, K, with topology coming with topology-induced by this absolute value is totally disconnected. And that's what I was saying. We were lucky that R was not totally disconnected. The moment you completed Q with the usual absolute value, it also became a connected nice space to do analysis. You do the same exact thing with p-adic absolute values, it's going to be a disconnected space. And there are solutions to that. But the solution that I like most, and it's most sort of available for the type of analysis that I want to do, which is like genuine hands-on integrals and things that I can relate to, is by Berkovich, which I will outline in the remaining of the time. My goal is to do 2 examples, but there's even a more basic example that I'm supposed to do. So I want to say what this is in the case of curves and abelian varieties. And my real interest is abelian varieties, but curves are also important because I like Jacobians too. So Berkovich's idea is actually a fundamental idea in 20th century that in order to understand the space, you better understand the functions on that space. This is a audience that should relate to. In order to make a scheme, you have to look at the ring of functions on that scheme. It's more important to understand that. But the idea actually comes from analysis. Gelfand already had spectrum for a compact Hausdorff space, he could reconstruct the space by looking at the space of smooth functions or continuous functions on that space by looking at characters. And that's the idea that we want to implement. So add points by looking at the space, at the ring of functions, let's say. Okay, let me do it in a concrete example. So, okay, in very short terms, you look at ring of functions and you look at the characters, but let me put characters in space quotes, characters of that ring. Because the word character actually is perfectly fine if you are over these unusual fields, but if you want to work more generally for arbitrary fields, you have to actually work with semi-norms. So let me do 3 examples. Probably I will have time for 2 of them. The third one is abelian varieties. Let's see if I'll have time for that. So let's say A1, the ring of functions that I should care about is polynomials in one variable. And so A1 over K is a non-Archimedean field. And as a set, so X is this, Xn is going to be a set. What I'm going to construct is actually a locally ringed space, but I'll go in 2 steps and then I'll give up. I'll say what is it as a set and what is the topology on it, and I'll not talk about the ring, the sheaf. As a set, it's going to be, okay, just here characters, but the correct definition of character is the following. It's going to be multiplicative semi-norms, multiplicative semi-norms, extending what I already have on K. This is a K algebra, so part of the elements on the ring, so multiplicative semi-norms on R. And I'm specifically actually writing it down. There's nothing in this definition, there's nothing special about R being this. You can write it for any spec R. You can look at the corresponding analytification by looking at multiplicative semi-norms. These are essentially like absolute values. I can write the axioms, but it's just a list of things. Maybe the semi means that it can have a kernel. So it's not true that absolute value of something is 0 if and only if. You can have more things that can go to 0. It's actually important to do that because you want a space that in good situations should be compact, and these are the extra things you should add. If you insist that kernels should be 0, you won't get, in good situations, compact spaces. Is it okay I don't list the axioms of multiplicative seminorms? Just think of absolute values with some kernel allowed.
You want it to coincide with a normal K.
That's what I said. It should extend absolute value on K. So if you give me a polynomial which is constant, the norm of that polynomial, I don't have a choice. I have to pick the norm that is.
Sometimes it's defined as terminating,
As what?
as being less or less than.
When you insist it's multiplicative seminorm, that's in the axiom. So you want, yeah. I think actually I've seen Matthias Johnson has written it a different way. I probably have looked at his notes. Yeah, I mean, yeah. What I've written on the board is correct. I think you can phrase it differently and prove that it gives you the same space. Okay, so this is as a set. I'm going to, maybe actually let me have a running picture. This was a totally disconnected space. I'm going to actually, I've added points, and I'm going to say what kind of points I've added. But in particular, I've kept my original points. My totally disconnected space is going to embed in this bigger space. It's going to give me, in a very natural way, multiplicative seminorms.
Are you assuming that K is already complete, right?
Yes, so for my application, it's going to be complete and algebraic closure. It turns out this also does completion for you. So if you just, it's a very robust completion. You can actually construct real numbers from rational numbers by looking at characters of the correct ring. It's a super completion. Yes?
Is it possible to do a definition of identification without considering a relative, without considering a ground state? Just the multiplicative.
So you want to identify rings, not just algebras, is that what you're saying? It is possible. It's not super convenient in Berkovich's theory, and adic spaces are more, you need, then you need a ring and some other R+, and then you have to be more careful. Then you can look at all possible valuations, not just rank 1 valuations. It is possible, but not the purpose of my applications, and probably Berkovich spaces is not. Okay, it's not true that one cannot do it. If you like, you can look at Jérôme Pauneau's thesis and other stuff. But in that generality, I would say go learn adic spaces. Probably you would be happier. Other questions? Okay, so this was as a set. I want to make a topological space. So topology is a kind of a weak topology. I'm going to put the, essentially if you think about it, there's only one natural way to put topology on this. It's going to be the weakest topology, which makes a whole lot of maps continuous, making all, so let's think of what kind of maps I can write. You give me an element of the ring, and you give me a, well, point in the space, I can write down this map. So this element, which is in my xn, can go to evaluation. So this was like an absolute value. It can compute a number for me in real numbers. And I can write a whole lot of these things. And I want all of them to be continuous. It's kind of a hard to imagine topology, but it's an easy to write down topology, right? Making all of these continuous. And OK, so this was a running example. I'm going to write down what you get for A1. And combinatorics enters the picture. But let me just say I did it for affines. There is a relatively complicated gluing theory. So if you have a general variety, you can pick an affine patch and then identify each one of them and then glue. Glue is not as easy as you think, but it can be done. There's also a more global definition. Maybe I say in words, you can, for any scheme theoretic point, you have this local ring attached to it, and your job is to take that local ring and replace it with all possible semi-norms that you can put on that local ring. So any point explodes into many points by doing, and that definition is not affine. That definition, you can do it for any scheme. So that would be more efficient, but I wanted to draw a picture for A1. So one can glue. I'll just write, one can glue spec Rs. You should trust me, it can be done. Okay, let me end the lecture by saying what do you get when you do this for A1. And immediately afterwards, as a corollary, I rely on your intuition from Riemann surfaces that curves are also very combinatorial objects. So let me just give you the way. For A1, you get some kind of a tree. It's a real tree. It's a little bit of a wild tree, but it's a tree. And we like trees. So for A1, for K of t, you have 4 types of possibilities. In fact, really, there are 2 concepts that I want to point out. And then 3 of them are coming from those 2 concepts. The first one is easy, or probably the immediate absolute value. If I give you 5 minutes, you will write these things. For any point in K, your job is what? I give you an element of the ring. You're supposed to give me some number, some real number. Let's try to do the most obvious thing you can do. For any element in the ring, well, you can compute f of a, which is the element of the ring, and take the absolute value of that. This is the absolute value on K. And you get a real number. Well, this fits the profile of the kind of thing I'm looking for. You check. In this case, it's super easy to check. This is, in fact, multiplicative semi-norm extending the absolute value. You can do it as I'm writing number 2 in your head. The second and third are really the same thing. For any element in the ring, let's pick a radius as well. Okay, this is going to be my radius, but let me qualify it in a moment. So you can do the following. I give you an element of the ring. You can look at f of z's for all possible z's inside this ball around A with radius r. And for all of them, you get numbers. Take the biggest number you get. So take the supremum, which happens to be maximum. Okay, now it's not super easy to see this is a multiplicative semi-norm extending the absolute value, but it's actually a consequence of Gauss' lemma in algebra. So this is to show that this is the right thing, this is Gauss's lemma. By that, I mean if you factorize a polynomial, yes. If you factorize a polynomial over Q, you get a factorization over Z, right? That's a lemma. Okay, it's exactly the same thing for type 3, except whether this R is an allowable output of absolute values or not is going to give you 2 different type of thing in the space that I'm trying to draw. So type 2 and 3 are really the same construction. It's just the constraint is whether that radius that I'm using is allowable or not. And type 4 is usually people say everything else, but that's a cheat. Here's an annoying, yet another issue that R and C were special. it follows essentially from Archimedean property of absolute value the following cute exercise, that if you have a nested sequence of balls in R or C, there is an intersection. The intersection of them is not empty. There is something in all of them. So you can imagine what I'm talking about. You have a bunch of intervals, and look at that they contain each other. In the limit, it's not going to be empty. This is not true in non-Archimedean world. So you can have a limit of nested balls that the intersection is empty. It's an annoying property. You can resolve it by going to spherical completion and other things. But in general, and in my field, this might happen. But there is an easy trick. You can look at for any of those balls. You can get their corresponding absolute value and look at the limit of those absolute values. So let me actually give names. So I'm going to call these eta A0 because it's like ball of radius 0. These two are eta AR. And this is going to be limit of eta ARs. If is a nested, that means I have to stop. I'm going to do that. Is a nested sequence with empty intersection. Okay, I can't say there is a ball there that I can write eta AR of that, but I can take the limit of eta ARs. That gives me yet another point. And the theorem is that that's all. For A1, that's all. And don't get too arrogant. That's pretty much the only ring that we can classify all its norms. A1 is the only case that we can write a list like this, to my knowledge. I've heard rumors that people are doing it for A2, but I have not seen a preprint. So let me just draw a picture, and I'm done. So you can now you can put a partial order on these things and draw is it called Hasse diagram when you have a poset? I'm going to do the continuous Hasse diagram of these, and you will see you get a tree. So say a norm 1 is bigger than or equal to norm 2 if for all f, norm of first one is bigger than or equal to norm of second one. Okay. So my original points were here, the totally disconnected space. And eta, if this is eta A0, and eta AR is going to be bigger than this, because not only I look at the f of A, I look at f of A and its surroundings. So, and take the biggest one. So this is going to be bigger. And I'm going to put an arrow to draw the Hasse diagram. And then for eta AB, B0, I can do the same thing. And the moment that I'm at eta A distance between A and B, the two balls become the same. So I get the same absolute value, the same multiplicative semi-norm. So these points collapse. OK? And then you do this. I'm not going to be able to draw this picture completely. I hope you forgive me. You have limited amount of time this week. But you get some kind of a tree in this way. It's a real tree. It has many, many, many branch points depending on your field. And it goes all the way to maybe missing a point infinity. So it's some kind of I would call it Hasse diagram of A1. OK? And you also have distance on this. So these points are infinitely far away, but you can actually say eta A, R, and eta A big R is this much away from each other. And in particular, these things are infinitely away because there's a 0. So it's a metric tree. I'll say it. I'm 2 minutes over. I'll say it, but I won't. I'll draw a picture next time. In Riemann surfaces, what is a Riemann surface? What is a complex curve? Locally, it looks like a piece of complex plane, right? Now, if I want to mimic that, locally it should look like this. A curve, a Berkovich-Riemann surface, a non-Archimedean curve, should locally look like a piece of this. If you have something that if you zoom in enough, you only see trees, if you zoom out, you might see a global topology. You might actually see a graph. So a Berkovich curve is going to be a graph and some hairy things like this going off to infinity. And number theory is happening at infinity. Combinatorics is happening at that finite piece, which I would soon call tropical curve. Okay? And for abelian varieties, there is a beautiful description that I'll start next time. So that's all.